Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the atomic structure. Today we will begin with lecture 16 from the course, but make sure you have watched the previous ones before viewing this one. Till the last lecture, we finished the discussion on the Bohr's atomic model, and I hope all that is clear to you because today we are going to apply all the concepts that we have learned into the numericals on the Bohr's model. These are very important. They are important from subjective as well as objective point of view. Many questions being framed from this topic. So please learn this well and do understand these numericals very well. They are going to really help you tackle any sort of problem on the Bohr's model. So the first question, this is on the photoelectric effect because I wanted to revise this with you again because we have to remember the relation that E is equal to h nu, that is hc by lambda. So we have the first question to be, if lambda naught, this is the threshold wavelength for the photoelectric emission, lambda is the wavelength of light falling on the surface of a metal, and m is the mass of electron, then calculate the velocity of the ejected electron. So the kinetic energy of the ejected electron, do you remember what is that? Yes, it is half mv square equal to h nu minus h nu naught, and this is going to be h into c by lambda minus c by lambda naught. So this is going to be hc into lambda naught minus lambda over lambda into lambda naught. We can write simply this again as v square to be 2hc by m into lambda naught minus lambda in over lambda into lambda naught, and from this you can calculate the velocity of the ejected electron to be the under root of 2hc by m into lambda naught minus lambda over lambda into lambda naught. The only thing I wanted you to remember this relation, so I have put it along over here, otherwise a very simple one. So now the next numerical that we have is for the Bohr's theory. So according to the Bohr's theory, the electronic energy of hydrogen atom in the nth orbit, this is given by En equal to minus 21.76 into 10 power minus 19 joules by n square. Calculate the longest wavelength of light that will be needed to remove an electron from the third orbit of helium plus ion. Right? So here the most important thing is that you have to remove an electron. Removing an electron means what? You have to take the electron to the level of n equal to infinity. Right? Because that is the place where the nuclear forces of attraction, they are going to become zero and the electron is going to be free. Right? So that is the crux to this question. So now let us see how we solve it. So for the hydrogen atom, the energy is already given to you. That is minus 21.76 into 10 power minus 19 joule by n square. For all other hydrogen-like species like helium plus lithium plus 2, what is the relation? We have the energy and you have to just multiply that by z square. Fine. The rest of the thing is same for hydrogen, but only you have to multiply by that square, and I hope you remember this. So now the energy for the third orbit of helium plus ion, what would that be? Helium Z is 2, so multiply by 2 square, and N is 3 because this is the third orbit, so we have 3 square. So this energy that is going to be there is minus 9.67 into 10 power minus 19 joules. Now the energy required to remove an electron from the third orbit, what it is going to be? Because your N1 is 3 and N2 is infinity. So delta E is going to be E infinity minus E3, which is going to be 0 minus 9.67 into 10 power minus 19 joules. Why? Because at infinity the energy is 0. Okay, I hope it is clear. So we have the delta E to be 9.67 into 10 power minus 19 joules. We have to give this much energy to the electron to completely remove it from the third orbit. So now delta E, this is equal to h nu. There has to be a definite frequency, and then again hc by lambda. This is going to be 9.67 into 10 power minus 19 joules. So you can easily find the wavelength putting the values of all the constants, that is h. Right, this is 6.626 into 10 power minus 34. C is 3 into 10 power 8. Delta E you found. So you will find the wavelength to be 2050 Armstrong.
The next question says that the wavelength of the first line in the BOHR'S series is 6561 Armstrong. Calculate the wavelength of the second line and the limiting line of the BOHR'S series. So the Rydberg equation you all know, 1 by lambda is R into 1 by n1 square minus 1 by n2 square. And what is the BOHR'S series first line going to be? N1 is always 2 for the BOHR'S series, and N2 because this is the first line. First line means the line of lowest energy transition, the lowest frequency, the longest wavelength. So please do remember all this regarding the first line. So N1 is 2 and N2 is going to be N1 plus 1 for the first line of any series. Fine. So for the first line of the BOHR'S series, if N1 is 2, then N2 has to be 3. Now it is simple putting of the values. You are going to get 1 over 1651. This is equal to R into 5 by 36. For the second line, now N2 is going to be 4. So 1 by lambda, which you have to find out the wavelength of the second line. This is R into 3 by 16. Now simply what you are going to do is divide the first equation by the second equation. And if you will solve, you will get lambda to be 4860 Armstrong. The next part is you have to find the wavelength of the limiting line. So for limiting line now, N2 is going to be what? It is going to be infinity. Right, the limiting line, the line of the longest frequency and the shortest wavelength. Fine. So we are going to get here 1 by lambda dash. This is going to be R by 4. Again divide the first equation by the third equation. You are going to get the lambda for the limiting line to be 3645 Armstrong. And from here you can even see that the wavelength of the first line, this is the longest wavelength, and wavelength of the series limit, right? The limiting line, this is the shortest wavelength. The next question says calculate the frequency, energy, wavelength of radiation corresponding to the spectral line of lowest frequency Lyman series in the spectra of hydrogen atom. Also calculate the energy for the corresponding line in the spectra of lithium plus 2. Again, the important point over here is going to be lowest frequency Lyman series. Lyman series N1 is 1. Lowest frequency, so this is going to be the first line of the series. So N2 is going to be 2. Fine. So this is what I want to stress in these questions. So if you are understanding this thing, then you are going to solve the questions very easily. Nothing as far as the calculations are involved. So 1 by lambda, you already know what is there. So for the first line of the lowest frequency in the Lyman series, N1 is 1 and N2 is 2. And again, if you calculate 1 by lambda, this is going to be 3 by 4 R. Put up the values, you are going to get lambda to be 1.216 into 10 power minus 7 meter. And if you have the lambda, you can calculate the frequency, C by lambda. So you get the frequency to be 2.47 into 10 power 15 second inverse. And Planck's equation gives you E is equal to h nu. Now you know the frequency also. You can calculate the energy also. This is going to be 16.36 into 10 power minus 19 joules. Now you have to calculate the next part, the energy for the corresponding line for the spectra of lithium plus 2. So if you have energy, For the hydrogen atom, you can find the energy for lithium plus 2 also by multiplying the hydrogen energy into Z square. So multiply this by 9, you are going to get 147.27 into 10 power minus 22 kilojoules per atom. Fine. So I hope this is clear. Again, the important point: lowest frequency, longest wavelength, shortest wavelength, first line, limiting line of the series. So these are the important terms that you have to understand. The next question says that suggest two transitions in the atomic spectra of hydrogen for which the wave number ratio is 108.7. So we know the wave number formula, that is again the Rydberg equation. So for the first line in the Lyman series, you have N1 to be 1 and N2 to be 2. Find the wave number. This is 3 by 4 R. For the first line of the BOHR'S series, what is N1? It is 2, N2 is 3. So we have the wave number to be 5 by 36 R. For the first transition in the Paschen series, N1 is 3, N2 is 4. Fine. So the wave number, that is 7 by 144 R. And if you calculate the ratio of Lyman to Paschen series, what is that going to be? 3 by 4 is to 7 by 144. This is what this coming up to 108 is to 7. Fine. So these two transitions, the first line of the Lyman series and the first line of the Paschen series, they have the wave number ratio to be 108 is to 7. The next question, and again a simple one: calculate the wavelength of the spectral line when the electron in the hydrogen atom undergoes a transition from N4 to N2 energy level, and then you have to tell the color of the radiation. So 1 by lambda known, we know that N1 is 2, N2 is 4, and 1 by lambda, if you are going to do all the calculations, you will find the lambda value to be 486 nanometer. Now I'll tell you the reason why I chose the question. Well, in many of the questions, because you have 1 by lambda and you have to find the wavelength, so what are you doing basically is you are doing R, converting it into 1 by R, right? So 1 over 1.09678 into 10 power 7. If you know this value, you have calculated it first and learnt it first, you are going to save a lot of time in your calculations. We have 1 by R value to be 0.912 into 10 power minus 7. Difficult to remember? No, it is not. Actually, this is 912 Armstrong. A easy number to remember. If you remember this, your calculations become easy. So we have 1 by R to be 912 Armstrong or 0.912 into 10 power minus 7, because that is what you are doing over here. So whatever way you write this, and then this is 64 by 12. So this becomes easier calculation as compared to this one. So the wavelength now it is coming as 486 nanometer, and you have to remember the range of the visible spectrum wavelength. So the color is going to correspond to the bluish green. Now calculate the kinetic and the potential energy of electron in electron volt if the electron is present in the Bohr's third orbit of the hydrogen atom. Fine. So do you remember the relationship between energy, kinetic energy and potential energy? While discussing, I laid a lot of stress on that is very important. Do you remember it? Okay, let us see what you can do about it. So kinetic energy of electron in the Bohr's orbit, this is going to be equal to minus of the total energy. Remember, both the magnitudes were the same, only the sign was different. So kinetic energy is minus of total energy. So for hydrogen atom, that is going to be minus 13.6 by n square and negative of that. So we get kinetic energy to be 13.6 by n square, and because we have to calculate for the third orbit, so n is 3, so we get the kinetic energy to be 1.51 electron volt. Now for the potential energy, remember the relationship: total energy was potential energy by 2, or we can say that the potential energy is 2 into minus of kinetic energy. So we get 2 into minus 1.51 equal to minus 3.02 electron volt. So please do remember the relation that total energy is potential energy by 2, and that is equal to minus kinetic energy. Very, very important. This is going to really help you. Now the next question is that if the ionization energy of He plus is 19.6 into 10 power minus 18 joules per atom, then find the energy of beryllium plus 3 ion in the second stationary state. So the ionization energy of helium plus, this is going to be the ionization energy of hydrogen into Z square. So ionization energy of hydrogen is what? This is the negative of minus the first energy for hydrogen, right? So E1 for hydrogen, and if you are going to put a negative sign in front of it, that becomes the ionization energy. So this is going to be 19.6 into 10 power minus 18 divided by 4, because we have given the ionization of energy of helium plus, divided this by 4, you get the ionization energy for hydrogen, and the energy for hydrogen atom, this is going to be the negative of this energy. So for beryllium plus 3 E2, this is going to be E1 for H into Z square by N square. So this is minus 19.6 into 10 power minus 18 joule per atom divided by 4 multiplied by 16 by 4. 4 is the Z for beryllium and N is 2. So we get this as 16 by 4. 16, 16 they are going to cancel, and you are going to get this as minus 19.6 into 10 power minus 18 joule per atom. Right? So I hope this is clear to you, the relationship between ionization energy and the energy, right? They being opposite to each other. Select the correct curve or curves. So this can be a multi-correct answer also. So you have to just think about it, what all you understand. I hope you can do this. You remember I told you that these graphs, if you have seen once, you will be able to appreciate what it is. Okay, your answers ready? Well, all these curves are correct. Let us see one by one. So we have V to be directly proportional to Z by N. So if there is a curve between V and 1 by N, this is going to be a straight line, right? Now for R and N, the relation for R is that R is proportional to N square by Z. So with N, the graph that is going to form is this way. Fine. Potential energy. Potential energy is directly proportional to Z square by N square, but this is the negative energy, right? So just like the total energy, potential energy is also negative in sign. So that is why you're finding the quadrant in the quadrant to be this quadrant. Fine. So we have a negative energy. So the graph is this, but this is also correct. Then for similarly kinetic energy, that is proportional to Z square by N square. So the graph you're going to get is this way. So all these graphs are correct, and please do try putting up different values of N and Z and plot the graphs yourself, so that you understand that these are the graphs which are being formed. They are very important. Children do confuse it lot many times, and that is why it is asked in the examinations lot many times. So please be very careful with them. Well, that would be all for this lecture. I've tried to put in as much as different variety questions, whatever was more important for you to remember from the BOHR'S concept. Fine. So in the next lecture, we would be starting our journey towards the quantum mechanical model. If you have any difficulty in understanding anything, any doubts, please do mail us at h2ochemistry@gmail.com. You can put your doubts or suggestions, anything in the comment section also. We would be glad to help you in any way. And that would be all. So have a nice day. Enjoy yourself. Please do click on the like link if you're liking the lecture. Do subscribe to our channel H2O, and also do click on the bell icon so that you get a notification as and when we put up a new lecture for you, a new course for you. Bye bye. Enjoy your study. Have a nice day.